Hello guys, how are you doing? I'm Mohammed Sadri, postdoctoral researcher at Microelectronics System Design Research Group of TU Kaiserslautern, Germany. And this is session number 7. This is video number 5. Video number 5 of session 7. And in the previous video, I created the internals of this module in RTL. I coded in Verilog, and in Verilog, in fact, I described the circuit that we will have inside this module. So it contained one multiplexer here, and then one sample generator, and we have now a kind of Verilog module that is not tested. And actually, it was my first time I was writing that module, and probably it has some problems, and we should verify the operation of the module, and we should solve its problems actually. So in this video, what I am going to do is that I am going to indeed first synthesize this block, because when you do an initial synthesis, usually it is useful because it shows you your major problems. I mean, for example, sometimes you do an initial synthesis and you see a large part of your circuit is optimized. Then you understand that some misspelling has happened, or the design has some problems, and in fact some parts of the design are not correctly connected to the rest of the parts, so some parts are optimized. Or obviously, if we have syntax errors, they will be indicated by initial synthesis. And so initial synthesis is generally a very good idea whenever you design something. Before going to functional simulation, even I would say a quick initial synthesis may indicate some important points to you, and after you did that, you go to functional simulation. So what we do, we here also create a sample test bench, and we test the operation of this unit, and we will look if it is acceptable, it's working or not. So I would like to, before going further, I would like to emphasize on the point that these videos are hobby videos. They are not official. They are just my own hobby to create these videos, and my goal is to help some people to accelerate learning and to be able to faster begin working with the ZYNQ device. And I see a lot of students, they ask me questions about how we should do this and how we should do that, and I see a big, in fact, a big advantage in creating these videos, since then you can really answer the questions that they ask you more accurately. So I should emphasize that the main reference is always the ZYNQ documentation, and you may like also to take an official ZYNQ training. I don't know, if you want to be sure that everything is correct. Okay, I go ahead and I come back into our famous folder which contains our design, and in fact I go to the Vivado folder. In the Vivado folder we have already one project that we created during session, I think session part 2, part 3 of this video, session 7. And now for testing my module, I create a new Vivado project actually, because I think that design is too big for having a test bench and for having an initial synthesis. So what I do, I think I will just call Vivado. Best thing I can do. Okay, Here I have the Vivado, and now you are very familiar with this environment and how it operates. So we begin with new project, and we just go ahead, and it will be called project 2 because project 1 is already there. So you just go ahead, RTL project, add files we will do later, we will do all of these later. I just press next, next, and for boards I select ZC706, but you can select whatever you like. So whatever ZYNQ device you like, you can select. Whatever board you have, you can select. There's no problem. Our designs are not that big, and right now we are not talking about PCI Express, for example, interface, or fiber optics interface, which are specific to ZC706. So we are talking about basics. So here I have the project, and as you know, I come to the tools, and I think I go to the project settings, and then when this is opened, I come to the IP and I add repository, and yeah, I clicked on this. Yes, yes, okay. Yeah, this is the IP repositories, and here I select my course folder, and I think I will select IP repo, and then I press select. And actually what Vivado does is it searches inside the folder and see if it finds any IP block. Yes, the sample generator is there, and that is it for now. The IP is added. So what I do right now, I just create block design, and I instantiate my new block into the block design. So here we have the block design, and here I can add IP, sample generator, double click. Sample generator is now here inside my block design. And for now, what I want to do, I don't add any other blocks to my block diagram. I just create interfaces for these ports. Okay, so for all of the ports and AXI interfaces, I create ports and interfaces because I want to only focus on this module right now, and later we delete those interfaces and we add other blocks. So here I come on my AXI slave port and I say create interface port, and it is an AXI. It's called SXIS, the interface, and it's an AXI S port, AXI Stream port, and it's slave, and I just press OK. So this is one interface is created, and my machine is a little bit slow. Okay, then we have MXI. Again, create interface port, MXI, AXI master, that is okay. And then we have a set of other signals here. For them we should create ports. They are not interfaces, they are ports. So I select this guy and I say create port. Okay, so it's not interface, it's the port. So it's called frame size, it is input, it's 8 bits. Let's have it. Now for enable I have to do the same thing. So again, create port, Yeah, enable input type is other. It's not clock, it's just a normal signal. No reset nor clock. For AXI enable, the same story. And for now I connect these two clocks together and I connect these two resets together, and in practice is the same. So for this module, as a kind of interface module, I don't have two clocks, I have just one clock and one reset. So I define this as a port, create port, and create port. We should wait. And this one is a clock port, and it has a kind of timing constraint on the port. So the port has also its timing constraint included, I would say. So this guy will be added, and for this guy I just connect directly these two together. Okay, so this is also clock. And then for this one again I need a port, and this one is a reset port. Okay, and then again I connect this reset signal to this reset port. Okay, my design is ready. So I would say the design is ready right now as of the tests that I want to do. And right now what I will do, I will come here, and for this block design I would do the procedure the same as what I have been doing every time. So we come to sources. Yeah, the system is, the link is very slow. Okay, we come to sources, design one, and first create HDL wrapper. And I want everything to be done by Vivado itself. So let's see if there are any errors or problems that we should solve. Yeah, we have two warnings. It says it says it's connected to an asynchronous reset. Yeah, that's not important. Yeah, the point is, in my code I should have used an asynchronous reset, not a synchronous one. But for now, suppose that the reset signal has a long enough duration and we don't have this problem. Okay, now kind of top level HDL is generated for our advanced design, and I go ahead and I generate output products. In this step, basically what Vivado does is it is copying the HDL code from the IP folder to its project folder. Okay, so it just basically does the simple copy. And for some IP blocks, of course, that are ZYNQ IP blocks, it performs the copy operations from the ZYNQ installation directory, or sometimes I think it has an automated way of producing code for some parts of the design. Yeah, the same two critical messages, they are not important. Now we reach one important step, and as I want to synthesize my design. And as I told you, the purpose is to see if very fast we can find any problem with the design before going to functional simulation. So what I do, I just say run synthesis. Okay, so far I have not seen any problem. I mean, any warning. Yeah, maybe there's no problem here, but in functional simulation we have a problem, and I think we have, especially with TLAST. But okay, now the dialog box opens and asks me if I want to run implementation, or I want to view synthesis reports, or I want to open the synthesized design. And actually this is one very important step. We will talk about it later, and this is obviously an important step. We will talk about it later, but for now, honestly speaking, I don't want any of these. So I just come here and scroll over the synthesis flow very fast to see if I find a specific warning or message, and it looks kind of fine, I think. So we go ahead and create a test bench for our design. So for creating test bench, I think we can come here to add sources. And then I think add or create simulation sources. Let's see if it works and solves our problem. Yeah, it says you can create files, add files, and whatever. I press create file. Hopefully it solves our problem. And the file type is Verilog. Yeah, we don't need system Verilog header VHDL. I think it's fine. And I call it sample generator test bench. Enter. Let's see what happens. But I'm a little bit in doubt if in fact this is the correct solution for what we want to do. Yeah, but let's finish. Okay, and now what I expect to see is I expect to see something in simulation resources added, in fact. Yeah, so Vivado wants us to define the interfaces of the module for now. I don't want to do anything special. Has not been changed. Are you sure? Yes. I want to then later design and in fact define the ports myself, so it's not necessary right now. Okay, so the kind of wizard is finished, and in simulation sources you have in fact a new file. Yeah, my network speed is very low right now, so I have my sample generator test bench here, and I have also the sources that I have generated in the main project, in the main RTL, also here. So it's just a pointer to those source codes. And what I want to do inside this Verilog file in fact I want to include this Verilog file, which is the top level of my design, and then I want to write some code, and then we will be able to do some simulations and to see our signals. So let's do all of these in Vim, because this interface is really slow. So let's find sample generator test bench.v. So here I have the lovely in fact bash, and what I do, I say find for me every Verilog file. Okay, it has found for me every Verilog file, and actually the thing that I was telling you about Vivado will just copy your HDL from the IP folder to its own folder. You can see it here. These are your files. They are now copied inside the Vivado. And then you may ask me, what if I want to clean this? For example, I want to make sure that there is no trace of my IP inside Vivado project, and I have changed something in my IP, and I want to be sure that the Vivado goes and again reads my IP from its main source. How should I do that? And okay, I think this is the first time I am telling this, but I should repeat this some more times. It's extremely important. There is one reset output products option here, and when you reset output products, then later you generate output products, they will be refreshed. And this is kind of very important tool. So when you have a very big design and then you begin changing, in fact, sub blocks, sub units inside your design, then you would like to in fact reset output products and regenerate them. So this is important. This is a very useful function, and I have seen, for example, several times you have a big design, you begin generating output products, and then Vivado crashes in the middle. And one thing that sometimes really helps is that you reset output products for the design and you regenerate everything from scratch. So let's go back to our design, and here I have the sample generator test bench. So what I need to do, I need to open this file, okay, and also I need to open the wrapper. Okay, so let's do it. Okay, Vim, I don't know if Vim will open two files in parallel. Yeah, this is the first file, and I need also the second file. So let's go to shell and I write down its name. This is the file that I need. This is my wrapper. Copy this, go back to Vim, and then open also this file. Yeah, so I have two files right now: the wrapper, the top level of RTL design, and I have also my test bench wrapper. Okay, and what I do, I just follow a very simple, in fact, methodology of testing the design. We don't want to do anything sophisticated right now, so I just copy, and then inside my test bench, I paste this block, and so I paste this block, and then I have in fact my test bench for now doesn't have any ports. This guy needs an instance, so usually you can call it whatever you like, DUT or whatever. So let's call it DUT, and then these are ports for the design actually. So we do the boring step of defining these as ports. These are ports, and yeah, there are some automatic ways of doing this, of course. And then you have, in fact, signals which are inside the test bench and will be connected, in fact to these ports, and for these signals I define them exactly with the same name of the port. So frame size, then T data, AXI T data, then it takes a lot of time, so let's make accelerate it a little bit. Yeah, forget about it, we don't accelerate. AXI T last, and please note that this, as the wrapper, as the top level of the design, this doesn't have any parameter. The one who has parameters is the guy which is inside the wrapper. This guy has parameters. Okay, so this guy has the parameters in which you can define the data widths, the start count, again the data widths for each of the AXI slave and master ports. But this, the other guy, the top level, which contains this guy, that doesn't have any parameter. In fact, the widths for these ports are indicated based on the parameters that you define here. Okay, we go back to our work. Yeah, so AXI ready, and if you have a good editor, what I do here is, I know with Vim also you can have block select and block copy paste, but I don't like it. Is so for anti-valid AXI valid, and then I would call this one clock. Okay, and this one I would call reset n. Okay, and so here is the name of the ports, and for each of these ports actually we need a variable. So reg AXI en, reg en, and reg, this guy is 8 bits, frame size, and then some ports are outputs. So wire, they should be defined as wires. AXI T data, wire AXI T last, wire T ready is the signal that we drive, and it should be a register. Reg AXI T ready, T stroke should be a wire, and actually since we had 32 bits, this will be a 4-bit signal. T stroke, then we have T valid, which is again a wire, AXI T valid, and then you have the set of signals for your AXI slave port, and let's also define them. So we have the T data, and it should be a register because we are driving this signal as AXI T data, and then you have, after T data, I think you have T last, so AXI T last, and then you have T ready, which is a kind of input for us. T ready for this, in fact the slave port is an input for us, and then after T ready we have T strobe and T valid, which are registers because we are driving them. So reg AXI T strobe, and this guy is, again, it needs to be 4 bits. AXI T strobe. Yeah, I know that these videos, they are kind of very boring. I know they are very boring. Yeah, you don't need to watch them, so you can just escape, you can just jump. And the most important registers, actually, I should define these two. Okay, I think they are complete. And yeah, so for now we don't want something really sophisticated, we want something very simple. So actually, let's make sure everything is correct. So far looks correct. So T valid is T strobe is T ready, T last, T data, they are okay. Then frame size, and then we have the enable and AXI enable. Okay, so begin. So initial begin. AXI EN, for now I put it as 0. EN, let's put it for a later time. Frame size, for now I put it as 16. Then for now I suppose that there is no activity on the AXI slave port, so I put AXI T data equal to 0, AXI T last equal to 0, AXI T strobe again equal to 0, AXI T valid equal to 0. Okay, I think that is it. And another initial block, begin. I want to define clock. So clock is initially 0. Let's have a 100 megahertz clock. And okay, if we are going to have a 100 megahertz clock, do we have any time scale? Yes, we have a time scale. So clock is initially 0 and then forever. What we do is we wait, I think 5 nanoseconds, and we negate the clock. Okay, let's have this for now. And then I need a, in fact, simple block for the reset. Reset n is 0, and then let's have it at 0 for 100 nanoseconds, and then it will be 1. I will remain 1 forever. And let's have something for EN. So EN is initially 1, and after, for example, 1000 nanoseconds it gets 0, it remains 0 for 100 nanoseconds, and then it gets 1 and it stays 1 forever. Okay, then what else? EN, AXI, and I think the frame size we define, the clock, the reset we define. I think we are addressing most of the important signals that we had here, and we are kind of ready to watch what will happen in our design. So let's save everything, and and go back to Vivado and see what happens in Vivado environment. Okay, yeah. So yeah, yes. So right now, if we look inside Vivado environment, and I don't know if I can, yes. If I look at a Vivado environment, sample generator test bench is the top in simulation sources. This is the top, and under this guy we have the rest of the design. This is because we instantiated our block as a design under test inside this block. Okay, and so right now I think we are kind of ready to run simulation. So let's just I press run simulation and let's see what happens. I don't know what will happen. Okay, run simulation, run behavioral simulation, and I have synthesized the design so I can do post-synthesis simulation, but for now the behavioral simulation I think is enough. So we continue. Yeah, let's see. Okay, so you have now the simulation environment of Vivado opened, and I think they call it iSim simulator, something like this. And this is not model sim, of course. This is ZYNQ's own simulator. Okay, and I think for the task that we want to do should be kind of enough. And the first interesting thing that I'm seeing is T-ready is always in fact X, and this is not good. Didn't we assign anything to T-ready in the code? Let's look. T-ready here I have defined as a register, but did I assign anything to T-ready inside my code? No. Let's do it. Okay, so here initial begin AXI T-ready, let's have it as 0, and then after 200 nanoseconds AXI T-ready is equal to 1, and after let's say 2000 nanoseconds message T-ready goes to 0, and again after 200 Mr. T-ready comes back. Yeah, no, this is the design, and the design is changed, so I think I have to close this behavioral simulation. Yeah, I have closed the behavioral simulation. I will run simulation again, run behavioral simulation, because our design, I think it needs to be kind of compiled for simulation again. It should be compiled again. So we should be a little bit patient. There is an error inside my yes, it says there's an error inside your design, and let's see if what is the error. Not line number 67. Yeah, AXI T-ready is not, yeah, obvious. It's obvious. I solve it. AXI T-ready. So ready, and AXI T-ready. Yeah, okay, let's go back. Again, we try again.